All right, so the last two sets of identities that we're going to learn and memorize and use for the whole year, we're going to meet today. And the first family is called the power-reducing identities. And it's a very appropriately named set of identities because guess what they do?
Reduce powers.
They reduce powers, right? Not like kryptonite to Superman power, but like make exponents smaller, okay? Which is pretty darn close, right? So here's what the first one says. It says that sine squared of 1x, okay, a squared power of sine of a 1x, it's equal to 1/2 the quantity, 1 minus cosine of twice x. You have to memorize that. What do you notice about that identity? What could you do then to help you memorize it? What are some things you recognize about it? Oh, yeah, there you go. That could help you. 1 minus cosine squared of x would equal sine squared. So that would be the PID, and sine squared is equal to 1 minus cosine squared. But this one is not cosine squared, it's cosine of 2x, but it kind of follows the same pattern. Of course, then there's a 1/2 out front, so if you want to memorize that, that's good. What else do you notice about it? Why is this called a power-reducing identity? It takes the exponent on the left, which is a what? 2, and expresses it in terms of a power of what? 1. That's cosine to the first. Okay? So that is why it's called a power-reducing identity. It allows you to write sine squared in terms of, well, here's the other thing you have to notice. It's in terms of cosine. Remember, cosine is selfish. He's trying to get into everything. He says, okay, cosine, I'm in. Now, here's the other deal. Because it's in terms of cosine, the trig function changes. The sign is negative. Okay, that's kind of the expense. So sine squared becomes a 1 minus cosine. And then what else do you notice happens with the angle? We start with an angle over here of 1x, and now it turns into a 2x. So here's how you can remember it also. We reduce the power by a factor of 2 at the expense of doing what with the angle? Doubling it. You half the power at the expense of doubling the angle. Half the power, double the angle. Half the power, double the angle. So you could even have like a sine to the 4th. And if you half the power, make it a sine squared, it'll double the angle. All right, so there you go. Look at the next one then. There's one for cosine squared. Cosine squared is equal to that, and that sure looks a whole heck of a lot like, on the right side, like the one we just saw. Is it? Yeah, there's a plus. That's really the only difference. Cosine is in terms of itself, so it gets to keep the plus sign. All right? So they're both in terms of cosine. 1/2 1 plus cosine of 2x. But again, it reduces the power by a factor of 2 at the expense of doubling the angle. 1/2 of 1 plus cosine of 2x. Now if you take the tangent, remember tangent is always just sine squared over cosine squared. So you don't have to really memorize this, but if you took this one here and you divided it by that one there, your 1/2s will divide out because they're common factors. And so you're just going to be left with the 1 minus cosine over the 1 plus cosine, and that's where this one comes in. But it comes directly from the ratio identity, so not something else to memorize other than the 1/2s divide out. All right, so this is pretty important if you go on to take calculus at any point, whether it's next year or, like I said last week, when you're 80, or sometime in between now and then, because this allows you to write powers of sine and cosine and even tangent in terms of single powers, and it's a lot easier to work with single powers, as you'll find out for sure next year. But let's get a taste of how this thing works. Example 5. Express sine squared of x times cosine squared of x in terms of a single power of cosine. A single power of cosine. Okay, so what to do first? You want to use the PIDs? Knowing that you have options is important, but then knowing which option to take is also just as important. Sine squared could be 1 minus cosine squared, but it's also equal to what we just talked about. So determining on what you want to accomplish, if I wrote it as 1 minus cosine squared, I would still have a power of cosine. So in this case, since I'm trying to write it as a single power, Maybe the power reducing identities are better than the PIDs. So let's go ahead and do that. Sine squared, I'll do in purple. That's 1/2 times 1 minus cosine of 2x. Good. And make sure when you write 2x, the 2 is on the ground floor. It's not small and elevated because that looks like squared. And then I'll use a different flavor here, boysenberry. Cosine squared is 1/2 times 1 plus cosine of 2 times x. All right, so now we'll simplify a little bit. I have 4 factors, the purple ones and the 2 blue ones. I will multiply like factors together. So 1/2 times 1/2 is 1/4. And then the other 2 factors, these guys here, those are very special factors. Those are conjugates of each other, yeah. And when you expand conjugates, you get a difference of 2 perfect circles. Squares, nice. Which means your middle terms will cancel. So let us do that. 1 times 1 is 1. Impressed? On your inside, you're going to get minus cosine of 2x. On the outside, plus cosine of 2x. Those will cancel. And so your last, you get a negative times a positive, which is negative. Cosine 2x times cosine 2x is cosine squared of 2x. All right. Did we accomplish our goal? Did we write it as a single power of cosine? No, because whether it's factored or expanded, it's still implicitly, when it's factored, a cosine squared. So now we need to get rid of that squared. Do we have a way to reduce the power of cosine? It's called the power reducing identity. So let's go ahead and let's distribute, okay? So we don't have to work with so many parentheses. This would be an option that you'd have. So if I distribute, I get 1/4 minus 1/4 times cosine squared of 2x. But now I'm going to focus in on this piece right there. And we get to use the power reducing identity once again. So this becomes a 1/4 minus 1/4. And then I'm going to go with the beefiest of all brackets. That's the beefy brown bracket. Okay? What is cosine squared of 2x equal to? Well, by the power reducing identity, it is 1/2 parentheses 1 plus or minus plus cosine of, very good, 4x. Okay? It doesn't matter what the angle is, you're going to reduce the power by a factor of 2 at the expense of doubling the angle. My current angle is 2x, so when I double 2x, I get a 4x. You don't always have to work with boring old angles of x. Half the power, double the angle. Whatever the power is, whatever the angle is. Half the power, double the angle. And now if I distribute, I'm going to go ahead and multiply those dudes together, staying with the beefy brown color. You get a 4th times a half, that's an 1/8, times parentheses 1 plus cosine of 4x. There's lots of little algebraic details here, so you got to be very, very meticulous. And now if I distribute the 1/8, the negative 1/8 actually, I get negative 1/8 minus 1/8 times cosine of 4x. And the very last thing we'll do is combine the 2 numbers in the front. What's a 4th minus an 1/8? Typical measurement on a tape measure. 1/8, yeah. 1/8 minus 1/8 cosine of 4 times x. And you're done. You have now written the original expression in terms of a single power of cosine. 1/8 minus 1/8 cosine of 4 times x. So next year, you really don't understand this now, but I'll show you. Next year we might be working with something that looks like this, if you take calculus. And you don't know what these symbols mean, but it's an integral with respect to x. As it sits right here, there's really not much we could do. We would just stare at it and go like, But if we know these identities, because sine squared cosine x we just said was equal to the following, 1/8 minus 1/8 cosine of 4x, now this is something that we can easily work with. And instead of saying, we're saying, heck yeah! And we just keep going, and we get the right answer. So that's why identities are so important. They can take an expression that is otherwise you're unable to work with it, and express it in something that is equivalent, but much easier to work with. It's a mathematical synonym. So power reducing identities, pretty sweet. Okay, now before we move on, you might be noticing that these are very, very similar to what we did on Friday. Of course, if you weren't here on Friday, maybe you don't pick up on that. Or maybe you're wondering to yourself, where did these things come from? Did they fall out of the sky? Were they imported from France? Where else have we had a cosine of 2x related to a sine squared, or a cosine of 2x related to a cosine squared? Yeah, the double angle identities. So let's take a look at that up here for a second. Remember, the cosine for 2x was equal to 3 different things. The only one that you really needed to memorize was cosine squared minus sine squared. That was the one that looked a lot like Papa Pig, but it wasn't. And then you can get the other two pretty easily by using Pythagorean substitutions. Okay? If you take, let's do this one. If you take the cosine of 2x is equal to, let's just do the bottom one. Let's write that right here. Cosine of 2x is equal to 1 minus 2 sine squared. If you're not trying to prove the identity, remember, then you're allowed to algebraically manipulate it however you want. So if I bring the 2 sine squared over here and the cosine of 2x over there, I get positive 2 sine squared of x equals 1 minus cosine of 2x. And now to solve for sine squared, I'll just multiply both sides by 1/2 instead of dividing by 2. And you get sine squared of x equals 1/2 times the quantity 1 minus cosine of 2x. And this right here is the power reducing identity for sine. And you could do something very similar for the cosine. So really, the power reducing identities are nothing more than the double angle identity for cosine solved for either sine squared or cosine squared. And remember, the double angle identity for cosine really came from the composite identity for cosine. So why would you want to memorize the double angle or the power reducing identity? Why not just use the composite identity each and every time? Because that's a lot of work to derive these things as you go, right? If you want to drive somewhere, you don't have to reinvent the wheel every time, right? You just get in a car that already has the wheels invented and are attached, right? So that's why. You're going to use them so often, they're useful in this version. So you can do the same thing for the cosine one if you like. Solve that for cosine squared and you get the other one. Sweet. All right, any other comments or questions about the power reducing identities? All right, they're pretty cool. Where can you go to practice these new identities? Yeah, if you want to memorize them, the Quizlet app again, Corpy_S space world, go to the one that says all identities, okay, and you can quiz yourself on them. But sometimes it's easy just to memorize patterns, you know, whatever. Okay, now the last set of identities that we are going to memorize for the whole year and use are the half angle identities. And these are my most favorite. They are the most fun. Fun. Or fun to the 5th. Or that'd be to the 6th. There we go. Fun. I guess of x. Okay, now these are also appropriately named. The power reducing identities reduce the power. Half the power, double the angle. Guess what the half angle identities are going to involve? 4th angles? 5th angles. No, half angles. Half angles. Very good. Half angle identities are going to involve half angles. So let's take a look at the one for the sine. Sine of not x, but what? If x is an angle, it's not sine of x, it's sine of half of x. That's where we get the name. Half of an angle x. Sine of 1/2 of an angle x is equal to, and this is part of what makes it so darn fun, plus or minus the square root of 1 minus cosine x over 2. And the cosine one, cosine also of half an angle x, is also equal to plus or minus the square root of 1 plus cosine x over 2. Anyone notice anything about these two guys? They are almost the same, but for what? The plus sign here for cosine and the minus sign there for sine. Very similar to the ones that we just kind of looked at? Notice the power reducing? Do these look at all like the power reducing? They do. In fact, this is exactly where they come from. If you rewrite the right side, by the way, 1/2 x is the same as x halves, just an FYI. If you want to prove that over here, 1/2 x equals x over 2. Right? If you don't know how to do that, tutorials. That's equal to plus or minus the square root of. Instead of dividing by 2, which is fine, you can multiply by 1/2, and you get 1 minus cosine of x. And the same thing with the cosine one. So this then, under the radical, looks a lot like what we just did on the power reducing identities. In fact, that's exactly where they come from. Let me show you. If we take the cosine squared one right here, let's say I want to solve that for cosine. Well, because it's squared, how do I solve for cosine of x? How do we unsquare something? Square root of it. So on this side, we get cosine of x. And, of course, when we take the square root, we have to consider what? Plus or minus. And so it becomes the square root of 1/2 times 1 plus cosine of 2x. So that's where the majority of the identity comes from. But this is written in a little bit different format than we want. So what's important about the power reducing identities, remember, was that if we started with a 1x, we did what to the angle? We doubled it, right? We doubled it. So the angle on the right is always going to be twice the angle on the left. But you can rephrase that, yeah? The angle on the left is always going to be what compared to the angle on the right? Half. X is always going to be half of 2x. So as long as that is preserved, you can make a substitution here. Instead of 1x and 2x, you can write it as, not with a highlighter, cosine of 1/2 x equals plus or minus the square root of 1/2 times 1 plus cosine of 1x. And that's still the same identity, because the angle on the right, x, is twice the angle on the left. So x is twice 1/2 x, just like 2x is half 1x. But the other way around, x is 1/2 of 2x, and now 1/2 x is 1/2 of 1x. So once again, this is just a little bit more useful version for what we want to use it for. But that's really all they are. The half-angle identities are nothing more than the power-reducing identities solved for cosine and sine with a little substitution on the angles. And then the tangent is identical to sine over cosine. Your 1/2s divide out under the radical, and you're left with plus or minus the sine one over the cosine one. Hi. Okay. So anyway, the thing about the plus or minus, whenever we're going to be using this, we can't leave it as plus or minus, because that would indicate 2 solutions, and we're only going to have 1 solution. So what makes this partly fun is the fact that we get to choose whether it's supposed to be plus or minus, and there is a right answer to that. So if you look down here, it says the sign of the radical, which you have to choose, will depend upon the quadrant in which the half angle terminates, okay, which is basically the angle we're starting with. We know how to figure out now pretty well where a given angle terminates on the unit circle. So let's say that 1/2 of x terminated in quadrant 2. In quadrant 2, sine would be what? Positive or negative? Positive, right? So we would choose the positive. But if we were doing cosine of 1/2 x, if 1/2 x terminated in quadrant 2, cosine is what in quadrant 2? Negative, so we would choose the negative. All right, so we have to choose if it's positive or negative. Let's try it out, shall we? Example 6. Find the exact value of sine of pi8. And then we'll do the other one. I'll set you up for the other one. Okay, the exact value. That means I can't go to the calculator and type it in. So the first things first. Is pi8 on the unit circle? Did we memorize that one? No, it's not. So we already saw with the composite identities that if it's not on the unit circle, we could still find the exact value as long as it's a multiple of 15 degrees or pi what? 12ths, right? If it's something pi 12ths, we know that we can find 2 angles from the unit circle that add or subtract to give us that angle. Is pi 8 a multiple of pi 12ths? No. Darn it. So we're not going to be able to find the exact value using composite identities. But is pi 8 half of a unit circle angle? It is. You can write pi-8 as 1/2 of twice pi-8, which is pi-4. So if you're ever given an angle, and it's not pi-12, if it's like pi-8 or something like that, if you double that angle, 2 pi-8 is pi-4, and that angle that's twice as big is on the unit circle, then you can write it as half of that angle that's twice as big. And what that means then is, using the half angle identity, you can find the simplified exact value. So here we go. Let's go ahead and find the value. Now let's get the sign first, the SIGN sign. Look at the very original problem. It says sine of pi-8. Which quadrant does pi-8 live in? It's the first quadrant, right? And in quadrant 1, is sine positive or negative? Positive. All of them are positive in quadrant 1. So we're going to go with the positive square root. I'm going to go ahead and write the plus sign down. You don't really need to if it's positive, but you do want to commit to whether it's plus or minus. Okay, so now we'll go with the identity. Sine of 1/2 x is equal to 1/2 of 1 plus or minus. Minus, remember, it's just like it was for the power reducing identity, cosine of twice pi-8, or right here, as you can see, pi-4. And there's the identity. Now, because we were able to write it in terms of pi-4, now we can evaluate it. So we could drop the plus sign out front, and we have a 1/2 parentheses 1 minus, what is cosine of pi-4? Square root of 2 over 2. Now at this point you have a numeric answer, but I'm always going to have you simplify these. This is where the fun, believe it or not, really begins. Okay, the fun really begins, because I'm going to have you rationalize your denominators. So what that means is two things. Number one, you should have no radicals in your final answer in your denominator. That's a pretty obvious one. But there's another way that that's implicitly accomplished. You should also then have no fractions under a radical. Because here's why. The square root of 3/4, although it doesn't look like you have a radical in the denominator, you do, because that's the square root of 3 over the square root of 4. Okay, so having a radical in the denominator is really the same thing as having a fraction under a radical. And I don't want your final answers to have that. So if you look at what we have, it is a numeric answer, but we definitely have a radical under, or a fraction under a radical. So here's how you're going to simplify this. Let's go ahead and make your Aunt Sally happy. Inside the parentheses first, we're going to combine the two terms. And of course, to combine two terms, you need a common denominator, which in this case is 2. So just call 1 2 over 2, right? And so you get 2 minus the square root of 2 all over 2. 2 minus the square root of 2 over 2. That's the same as 1 minus the square root of 2 over 2. And now we'll just multiply straight through with the 1/2. So 1 times the numerator gives us the new numerator. And in the denominator, 2 times 2 is 4. Now you got to be careful with your radical here. This radical still encompasses the whole thing. So we still have a fraction under the radical, which is no good. But now since we have a single fraction, we can use the property that says the square root of a over b is equal to the square root of a over the square root of b. So we'll give them each their own radical. So that is now the square root of 2 minus the square root of 2 all over the square root of 4. And now we don't have a fraction under a radical, but we have a radical in the denominator. It's really the same thing. Now, we don't have to rationalize this. We don't have to multiply by square root of 4 over square root of 4, because in this case, the square root of 4 is also known as 2. So you end up with 2 minus the square root of 2 all over 2. And that's not a bad answer. But here's another way to write it, and this is how I kind of prefer to write it. 1/2 times the quantity 2 minus the square root of 2. They're equivalent. Now, you will end up with a radical under a radical, and that's okay. That's actually kind of radical. But because you have a radical under a radical, having a fraction then makes it look a little bit kind of complexy, which is why instead of dividing by 2, I would prefer to pull the 1/2 out front. So now it looks like a coefficient instead of a denominator, but they're equivalent. So 1/2 the square root of 2 minus the square root of 2, and notice it makes a big difference where your radicals are and which radical covers what. That is your simplified rationalized answer. There are no radicals in the denominator, and there are no fractions under that radical. And I claim that that is the exact same value as sine of pi-8. Now, why did we choose positive up here to begin with? Pi-8, yeah. It's not where pi-4, the angle that's twice as big, terminates. It's just where the original angle terminates. That's going to determine the sign. So here we go. Let's verify it. We're going to go to the calculator now, and you should be in radian mode, so check your mode, radian, there we are. And let's go to the home screen, and we'll type in sine of pi-8. Should this number be closer to 0 or closer to 1? 0, right? Because sine of 0 is 0, pi-8 is just a smidgen off there. We hit enter, and we get 0.382. Yeah, okay, sweet. That's perfect. Now, if we type in this answer here, it should give us the same thing. And if it doesn't, then we just tell stories the rest of the year, right? Because math is not worth studying if this is not the same. Now, maybe we made a careless mistake, but I doubt it. Now, in the days before math print's beautiful because you can clearly see where the radical starts and ends. But in the days before math print, you had to put parentheses to enclose all your radicands. And it got a little bit confusing, you know, opening and closing your parentheses at the right time. So with math print, y'all are spoiled. You don't even know how spoiled you are. Spoiled. Of course, your grandparents are like, calculators! Y'all are spoiled. I would have looked forward to knowing where to put a parenthesis before math print. They had to use like abacuses and stones to count. Maybe not that. No, they used slide rules, which is kind of a lost skill. Anyway, I'm just pausing for dramatic effect. If I hit enter, it should be the same, right? Oh, yeah, it is. Yeah, it is. That is. It's exactly the same. I think that deserves a little round of applause. That's pretty awesome. Yeah, sweet. Okay, clapping for math. Let's go ahead and have y'all then do cosine of 7 pi-8. But oops. I'll set you up, and then y'all can do the fun part on your own. The fun part is the algebra and rationalizing. Cosine of 7 pi-8. Want to find the simplified exact rationalized value. Is 7 pi-8 on the unit circle? No, it's not. Is it a multiple of pi-12? No. If it were, we would use composite identities. But is it half of an angle that's on the unit circle? Is it something pi-8? Yeah. So we are going to be able to use the half angle identity. So here's how you can figure out the angle. It's going to be cosine of 1/2 times double that angle. What's twice 7 pi-8? 7 pi-4. Okay? Now 7 pi-4 is on the unit circle. It lives in quadrant 4. But when we go to the identity, we want to know where the actual angle that we're working with lives, which is 7 pi-8. That's what we call the half angle. Where does 7 pi-8 live? Quadrant 2. Because remember, pi is 8 pi-8. So we're stopping just a smidgen short of the x-axis, the negative x-axis. So in quadrant 2, cosine is what? Negative. All right, so we're going to go with negative square root of, and then 1/2, 1 plus or minus. Should be plus, right? Cosine is selfish. It's in terms of itself, so it's plus, bless you, cosine of 7 pi-4. All right, so from there, I want you to simplify it down to a rationalized answer that's exact. All right, no radicals in your denominator, no fractions under your radicals. Very similar to what we just did. Bless you. Where'd your negative go? Oh, yeah. Yeah. Don't let that negative fall away by the wayside there. It should be out in front on every single term. Remember, your next test, there's no multiple choice. It's all open-ended questions. So if you lose it at any step along the way, you'll lose a check. Every line as you work down has to be equivalent to the one above and below it. You still have a... Oh, yeah, okay, I thought that was squared. Yeah, that looks good. Looks good. Yeah, here, if you run out of room, just start another column. Let me see if I can catch up with y'all. So as we work down, if you work straight down with an expression, you don't really need equal signs. The only time you need equal signs is if you offset it, like if you work horizontally on the same line, and you say that this is now equal to that. Now as you work down on the right side of the equation, that's where you would need equal signs. Okay, just kind of an FYI. But if you start with an expression and you just work straight down, then you really don't need equal signs. All right, so we got minus square root of 1/2. Cosine of 7 pi fourths is positive or negative? Positive. So that number could end up being negative depending on where that double angle lives. But in this case, it's quadrant 4. The negative up front is because our angle, 7 pi eighths, is in quadrant 2. And now if we do your Aunt Sally's rule, in the radicand, in the parentheses, you end up with 2 plus the square root of 2 over 2. And you can go straight from that step to that step. That's great. And then if you multiply, you're going to get 2 plus the square root of 2 all over 4. And just make sure that your radical extends all the way down to cover the whole fraction. And then from here, if you want to go straight to your final answer, I'm okay with that because the denominator, they're each going to get their own radical. The denominator is the square root of 4, which is 2. So dividing by 2 is the same as multiplying by 1/2. So if you want to go straight to this as your final answer, that's good. But just make sure that your radicals, your symbols, cover everything they're supposed to cover. Don't make them too long. Don't make them too short. Too short is almost too bad. But sometimes too long could be equally as bad if they're the first term. And there's your answer. And if you want to type it into your calculator, you'll see that you're correct. You're awesome. Well done. Okay, so we're not going to go to example 7 today, but I do want to introduce you then to that bonus opportunity. So you've been waiting so patiently. Yeah. Okay, so here's what your bonus opportunity is going to be. And you can do this outside of class. I don't know exactly what day your test will be, but this will be due on the day of the test. You're going to find, if you choose to do so, the simplified, exact, and here's the fun part, rationalized value of tangent of pi 30 seconds. This is a bonus that Mr. Peck used to do back in the day when I was one of his students. And ever since I've been a teacher, I've just kept it going. It's a fantastic problem. If you can successfully get the simplified, exact, rationalized value of tangent of pi 30 seconds, and by the way, you have to show all the steps, then it's almost enough for you to show that you understand the whole chapter, okay? Because this can take, I don't know if I've had too many people fit it on one side of a page of paper. Usually it takes 2 pages, sometimes 3 or 4 pages, depending on how you work. But it's a fantastic problem. It's going to be a positive number, okay? there's a lot of things to do here. And you're going to have so many radicals under radicals under radicals under radicals that it can get a little bit kind of confusing. But once you think you have an answer, so that there's no radicals in a denominator and no fractions under a radical, then type it into your calculator in radian mode and make sure you have the right answer. Don't just turn in garbage to me, because there's no partial credit. But if you get it correct, it's going to be worth plus 10 on your next test. And sometimes I like to say, if you turn in something that's not correct, I'll take 5 extra points off your test, because that's just wasting my time. Because to type it into your calculator to see if it's right, that takes a little bit of effort. Okay, and I have to do that with y'all's paper because there's a couple of different versions of the right answer. But again, with math print, it's a lot easier than it used to be. When you have like 5 embedded radicals, like a term plus a radical underneath another radical, the parentheses used to be the big obstacle to checking it. But now with math print, it's a piece of cake. Okay, so make sure you check it if you think you got it. It's due on the day of the test, which will be next week sometime. Now let me give you a little smidgen of what this is going to look like in the time that remains. Let's just start off with tangent of pi 8. Now, tangent of pi 30 seconds, you're going to be able to do with half-angle identities, because pi 30 seconds is half of pi 16ths. And pi 16ths is half of pi 8ths, and of course, pi 8ths is half of pi 4ths. So that's why you're going to have to use that half-angle identity many times. So tangent of pi 8ths is the same as sine of pi 8ths over cosine of pi 8ths. So this would be kind of your first step with pi 30 seconds. And now that's the same as sine of 1/2 of pi 4ths all over cosine of 1/2 of pi 4ths. So now if we use the identities for both of them, the sign is going to be pi 8ths and pi 30 seconds are all in quadrant 1. So these are all going to be positive square roots. So we get positive square root of 1/2 times 1 minus cosine of pi 4ths. There's the numerator. And the bottom is going to be the square root of 1/2 times 1 plus cosine of pi 4ths. And now, if we start simplifying that, you could put them underneath the same radical if you wanted, and the 1/2s will divide out. Okay, I'm not going to show that step, but your 1/2s will divide out if you put them under the same radical. So really, we're left with the square root of 1 minus cosine of pi 4ths, the square root of 2 over 2, all over, and this is what the tangent identity actually is. It gives you without the 1/2s there, all over 1 plus the square root of 2 over 2. So there's the numeric answer, but it's ugly. You got radicals in the denominator, and you have fractions under radicals. So if you simplify the top and bottom, kind of like what we just did, you'll have a 2 minus the square root of 2 all over 2, all over 2 plus the square root of 2 over 2. And now if you give them each their own radical, you get the square root of 2 minus the square root of 2 all over the square root of 2, all of that over the square root of 2 plus the square root of 2, all over the square root of 2. You see that? This is just pi 8ths. This is not even pi 16ths. Which much less is not even pi 30 seconds. I'm just, in the top, I'm giving each numerator and denominator their own radical and the denominator. And why would I want to do that? Because now I can stay change flip. And what happens with your square root of 2's? They will divide out, and you're left with the square root of 2 minus the square root of 2 all over the square root of 2 plus the square root of 2. And now the real fun begins. Because now I have a radical in my denominator. I have the square root of blob. How do you get rid of the square root of a blob if it's a single radical? No, the conjugate is not going to be until I get inside the radical. Right now in the denominator, I just have the square root of a single quantity. So that's when I multiply by just that same radical. Not the conjugate yet, right? Because it's just the square root of a single quantity. So it'd be like 1 over the square root of 5. You'd multiply by square root of 5 over square root of 5. All right, so this is just that itself. Now, in the denominator, what is a radical times a radical? It's the radicand, yes? It's just the radicand. Now, in the top, because I have the square root of a times the square root of b, I can call it the square root of ab. Which, why would I want to do that? Because underneath those radicals, I have what conjugates? Conjugates. So look what happens here. If I put them under the same radical, and I expand them, 2 times 2 is 4, and then minus 2 square root of 2 on the inside, plus 2 square root of 2 on the outside, those cancel, and I'm left with minus square root of 2 times square root of 2 is 2. So that's putting the top under the same radical and distributing. So now if I simplify, I get the square root of 2 all over 2 plus the square root of 2. And I'm almost there now. Now I have another radical in the denominator, but now it's 2 terms, so now I multiply by the conjugate over the conjugate. And in the bottom, you're going to get 4 minus 2, and in the top, if you distribute, you get 2 square root of 2 minus 2. Well, of course, 4 minus 2 is 2. So if you then divide out the 2 from each term, I'll factor it out. You do that. Now your 2's divide out. You're left with the square root of 2 minus 1. So notice how ugly it was in the beginning, but how pretty it turned out to be in the end. The real fun is in the rationalizing. And that's just pi 8. If you do it for pi 16th, it's like exponentially fun. You would think it'd be twice as fun, but it's actually like a 16 times fun. And if you do it for like pi 32nds, it's like 296 times more fun. That's awesome. Okay. We'll pick up there tomorrow. We'll finish the notes. Have a great rest of the day.